Dr. Sayali has completed her MS and PhD in reproductive biology. She has many certifications and certification in clinical embryology, PGT, PGF, embryo biopsy certification, and presently she is a research scholar enrolled in
this is excuse me. I think this is the wrong speaker. I think I am the one presenting.
Sorry, sir. I am introducing the moderator, and she will introduce you.
Okay.
Okay.
Thank you.
She is a Chief Scientific Officer, Celsior Biotech and Research Center, India, and she is an advisory panel, and she is an on-site, off-site laboratory director for 7+ IVF centers across India. Over to Dr. Sayali. I request you to introduce speaker of the day.
Thank you, Dr. Anandalakshmi, and I welcome Dr. Nabil Arrach. It is an honor and pleasure to have you in MBOT 4.0. We have interacted before in person, and it is absolutely a pleasure to moderate your session. Let's go on to the introductions. Dr. Nabil Arrach is PhD MBA, and he is a founder and CEO of Progenesis, which is in US, California. It is a note that Dr. Nabil Arrach was one of the first people, one of the
Like you are muted.
Shall please unmute yourself?
Oh, I'm sorry. I will start again. It is an honor and pleasure to welcome Dr. Nabil Arrach. I hope everybody can hear me now. He is the founder and CEO at Progenesis US, California. He was the first person to validate NGS for PGTA, and that's a very big achievement back in the US. He has had numerous research grants from NIH and many new inventions and discoveries coming from Progenesis US, as we know. So it is our honor and pleasure to welcome you, Dr. Nabil, and please continue with your talk.
Thank you so much. Thank you for the introduction, and thank you for the invitation. Pleasure to be here with you guys. I am about to share the presentation. So let me see if I can. Very good. So today we're going to be talking about, am I audible, clearly audible? Perfect.
Yes, Dr. Nabil, you're audible. Yes.
So today we're going to be talking about non-invasive embryo screening with metabolic profiling and machine learning. But before I delve into that conversation, I would like to talk a little bit about the status where we are with PGTA, with biopsy. The PGTA today is still the gold standard compared with non-invasive. Correlation-wise with embryo, it's about 95%, although this number is hard to really estimate because it doesn't take into consideration all the implantation, pregnancy rates, and all the variation that comes with it. It's hard to really predict the accuracy of PGT. Mosaicism still a big issue in PGT. As we see, there are labs that report mosaicism at very high rates, ranging somewhere between few percentages all the way to 20% or over, and that poses a challenge for physicians and embryologists and patients to choose the right embryo to transfer. And the implantation rate is in about 70% according to the average clinics, US, at least in the US side. The biopsy, it's a very highly complex procedure. We have seen that in many countries around the world as we go. We see that the training and the proficiency to do biopsy, it's still a difficult task for embryologists. It's not very efficient because, managing a high number of cycles with biopsy, it poses a challenge for the embryologist. It takes time. It could be potentially damaging, and that depends on the expertise of the embryologist and the resources available to the clinic. we have published the first non-invasive PGTA with genomics a few years ago, and after many years assessing the literature, we see that when you look at all the literature combined, the correlation between the media and biopsy, it's about 80%. And we've seen a limitation in the genomic tests. One of them is the fact that the material contamination tends to overcome or overwhelm the amount of DNA available in the sample. So let's say if you have a samples with a high amount of material in cumulus cells, and it tends to overpower the nuclear DNA coming from the embryo, and that generates a miscall or a false negative. So gender accuracy in genomics using non-invasive tests, it's about 10% or a little higher than 10%. So this obviously does not reach the clinical, the clinical rates that a lab can provide to offer this for patients. And so we've been looking for other alternatives. One of them is the metabolic profiling. And why metabolic profiling? Because when you look at genomics, it's really a one-dimension analysis. It's you look at number of chromosomes in an embryo using media, and then that doesn't really translate into the ability of embryo to implant. It tells you this embryo is euploid, has the potential, but it does not tell you it's biologically capable of implanting. And I think that's the critical difference between a metabolic test and a genomic test. In metabolic tests, you look at how embryos metabolize peptide, what the rate of conversion of sugar. You can look at what hormones they are secreting in the media, and are they suffering any stress? You can measure stress molecules. You can look at cofactors such as NADP and FAD. And so it gives you a holistic picture of what the embryo is like, biologically speaking. And I think that is what makes it so unique in determining the ability of this embryo of implantation. Obviously, there are other factors that are outside of the embryo, such as endometrium and the patient's preparation aspects and all that, but the embryo, as far as the embryo goes, it gives you the whole picture. And so embryo goes through a range of pathways and metabolism during the first 5 or 6 days of growth. And so if you try to pinpoint a specific metabolite, it will be virtually impossible. So you have to have certain ways of analyzing all these complex pathways. And the only way to do it is machine learning. Because if you think about it, in the 80s and 90s, and the way metabolism was studied is by looking at specific peaks, specific metabolites, but really you never get the whole picture when it comes to metabolic activity. If I want to summarize this in a nutshell of what the metabolic test will offer that a genomic test is not able to offer, it would be that the metabolic test does not depend on the DNA. And therefore, if there is material contamination, that would not be a limitation to deal with. And therefore, the misdiagnosis of gender and other things. I know that in India, gender is not permitted, and in other countries, but it's still a misdiagnosis. So meaning that it could also affect other chromosomes. And so the other things is that the sensitivity of the test, it's way higher than genomics, because the way you do the sampling of the sample is very sophisticated For example, with the metabolic test, you can sample 100 of mini samples or micro samples in the same drop. And this is one of the equipments, mass spec equipment that capture that test. Basically, the sample is ionized on a drop, just like a micro drop. And then samples after ionization, it's bombarded by lasers. And then the molecules, the ions will fly through the equipments, the tube, and the time to fly, the time they reach the sensor, it determined the mass and the charge. And so one way to really get the best out of the metabolic test is to be able to look at these in combination with other tests. Since spent media has its own limitation, spent media, it's not very consistent across lab and within labs and across embryos. You have to have additional perspectives to look at that media. Genomics is one of them. The people have tried in the last few years. Embryo images, AI, it's another aspect. Both genomics and embryo images have given us about 80% correlation as a industry, research industry. And so if you add metabolomic, it's going to definitely give you a better perspective of looking at an embryo. So the idea is to try to combine multiple perspectives to assess an embryo. So this is a typical plot that you would obtain with mass spec. So in one color, you have the media, the culture media, and in the second color, you see the embryo. And they are superimposed so that you can see the differences. So if you try to select specific peaks, a small number of peaks, and you try to establish a correlation between certain peaks and euploidy and implantation, it's certainly going to be a limited approach. And that's what scientists have tried in the past. We didn't have the ability to look at data from machine learning perspective. And so we didn't use any sophisticated algorithms. We tried to use algorithms that are looking at specific peaks, small number of peaks. And that's why in the past, metabolic tests has not been as successful. We've done a study where we have a multi-research study. We have looked at more than 200 patients, of which 150 were analyzed with the multi-spec, and then that data was extracted. It was normalized using, industry algorithms, and then the data was pushed to machine learning algorithms for data training and testing. The remaining 50 samples were analyzed with high resolution mass spec to identify the exact molecules that are different between these samples that are euploid and aneuploid, and male and female. And so this is the machine learning model that we've tested. There is a number of data testing and training, evaluation, and then after that we go into the model or modeling and prediction. So we have tried different models from decision tree to random forest, logistic regression, and we end up using dense neural network with some classifiers. And the accuracy obviously depends on the model. And you have to, in machine learning, you have to really try different models and try to refine them as you go, maybe with more data, to try to find the best model that suits the type of assay that you are developing. So the prediction that we've received or have seen with this, looking at the PGT results, euploidy, and the prediction was between 86 and 94%, 94.8%, but on average it was 90% given all the all the characteristics that we were trying to look at, but it's still much higher than genomic tests, and we think that combining this test with other tests could lead to a clinical test that you could provide to patients. So the second component that we've been working on is embryo images, trying to establish a model where you can predict euploidy using images and neural network. We are in that 70 to 80% range, depends on the model that we're using. The idea is to get to a combined report or combined test where you see the non-invasive PGT in one column, then you see the metabolic test, and then you see the AI score, which is the quality of the image and how it correlates, and the morphokinetics, and all that could be combined into a single score, a ranking score, to establish the priority, what embryo could be transferred first. And I think this is going to be probably the best approach to assessing non-invasive media. To end, I just want to introduce GENES. GENES is an annual symposium that we organized in June. The first symposium was last year in San Diego, California. It's a very interesting symposium that tried to gather experts in genetics, in biology, and endocrinology in one meeting. So you're welcome to ask or inquire any information about GENES. And with this, I am reaching the end of the presentation. Thank you so much.
Thank you, Dr. Nabil, for this wonderful presentation. It was really eye-opening to see new data that is coming from your laboratory. And I think this might be, for many people, including seniors, the first sort of glimpse of how metabolics could be incorporated with genomics, non-invasive genomics, and along with AI assessment of time-lapse imaging. So absolutely, thank you so much for your inputs and sharing your research data with us. I have a few questions, if you don't mind, before we can move on. The first question that I had was that, as we know, non-invasive is now, I mean, at least the research data is coming up and it's becoming more and more promising in the last 10 years. And the first thing, and because AI is also working side by side and evolving in part because of practitioners and companies like you, my first question is the data sets that we have. How many data set points did you have for running the ML algorithm for the NIMA test?
The data that we had was not too big. It was about 200 patients or samples. But we are in a study, multi-research study now, gathering much bigger sample, because we know that it's going to end up being, that's for the mass spec. As far as images, we have thousands of samples that we have analyzed. But we are in a second phase research study, gathering much bigger sample and looking also at the way of whether this is going to be personalized by center, because some centers have different media. You know, the media that they are using, they have relatively different metabolites, and they could also be culturing a little differently, which could also cause the metabolism to be different. So this is not something that we have seen in the past. I think it could be valuable to look at those variables between organizations, between labs, clinical labs, IVF labs, to capture that variability. But that's the intention.
Absolutely, I do agree that that's a long road, because the variables that you must have done already for non-invasive PGT, because as you know, non-invasive PGT is so challenging, started at low 60s in concordance, and now it has reached to late 80s, and there are multiple labs struggling or trying to optimize. So my next question is in non-invasive PGT, because you're very experienced in the same, and we have done some work alongside in India. Is the fact that there were a couple of studies that were presented in ESHRE talking about how the culture media manufacturers themselves, they are not creating DNA RNA free medium, and there are small genetic components, small fragmented DNA that is still present in the culturing media. Do you think that is something that might affect a lot by lot variation for NIPGT, especially in labs, genetic labs that are not standardized to do NIPGT? What are the parameters that a clinical practitioner, a clinical embryologist, or a clinician should look out for when they're sending NIPGT? Because in India, unfortunately, we don't wait for data. Sometimes patients are subjected to tests without the test really being optimized. So please, your inputs.
Yeah. I see the biggest limitation in genomic tests, PGTA and genomic tests, is that there is no consistency between samples. So the assumption is that you are relying on some embryos to partially lyse during that cell division. So when you reach a stage of 100 cells or more, some of the cells will lyse, just part of the natural process of growing, and then that will make some of the DNA available to testing. But not every embryo behaves the same way. In fact, many embryos, there's lots of variability within the lab and even within the patients. And so I think that's the culturing system that we currently have has not been designed to capture DNA. It was designed to preserve the integrity of the embryo. And so that there's a conflict there, right? It's like
I think that
yes.
Yeah. I think that interest conflict is something that multidisciplinary challenge for the entire industry. If we want NIPGT to succeed, and if you want even NIMA to come in, because we do believe this is the future. And as a practitioner using time lapse in the last 10 years and using PGT, I'm really excited to see what you bring in. And we hope that some of the research from India also makes its way with you. And thank you. If there are any questions in the chat box, I will just go through it. Currently, we don't have any questions in the chat box. Thank you, Dr. Nabil, and thank you so much for sharing.
Thank you.
Ananta, you're muted.
Thank you, Dr. Sairi. Thank you, Dr. Nabil.